Welcome back to the discussion of spatial networks. In last 4 videos, we looked at the societal motivation. For example, many of us use navigation apps on our smartphones, also via web services such as Google Maps. Underlying these applications, we have many spatial networks such as road maps, public transportation networks, and so on. We also looked at conceptual data models for spatial networks. For example, we looked at entity relationship diagram, which can represent a rich set of concepts. For example, in road map, one may represent streets, street intersections, turns, points of interest, and so on. Mathematically, we use a simpler model called graphs, which essentially consists of a set of vertices or nodes and another set of edges. In case of road maps, the vertices may represent road intersections, and the edges may represent road segments connecting those. Okay. Now, next we started looking at logical data models, primarily for querying road maps. And we discussed why the SQL we have learned so far, the spatial querying we have learned so far is not adequate. Okay. Formally, relational algebra cannot represent transitive closure, so you need some new things. So, in this video module, we are going to learn one extension to SQL to query graphs. Okay. So, at the end of this video, we should all be able to describe the connect clause in SQL select. It is a vendor specific feature. Oracle was one to start this feature. There may be other brand names which may also have it. And using connect, we will also learn how to query a directed acyclic graph. So, here is your quick background. You remember for querying, we learned that our traditional SQL, which is based on relational algebra, is not capable of computing transitive closure. In other words, if I gave you road segments connecting adjacent road intersections, we cannot express shortest path query in old SQL. Okay. So, we need to extend SQL to support graph queries such as shortest path, and there are two broad ways to do that. One could use abstract data type in SQL3, very much like the OGIS data type, points, polygons, etc. we used for spatial querying. One could define graphs and paths, vertices, edges, and so on. Okay. The other approach is to add custom statements in SQL, and we will start from there first. Okay. So, there are at least two different ways people have done it. We will look at the original connect by connect clause in select statement that was popularized by Oracle, and then in the subsequent video you will come back and look at recursion, which is standardized with SQL3. Okay. So, without further ado, let us look at the connect by facility, and in this slide we are going to look at the input and output. And as you recall, the goal is to compute transitive closure. So, input is a graph, more specifically a directed acyclic graph. So, for example, here we are showing you the river network represented as a graph, where the nodes are rivers, such as here you see Missouri, Mississippi, and the edges, directed edges represent falls into. So, Missouri falls into Mississippi, and that is this edge. Okay. Given such a graph, the connect by statement can compute transitive closure. In addition, it can actually give you a subset of transitive closure. So, for example, you can specify a start node. Let us say we started with Missouri, then we can do two kinds of queries, either predecessors of Missouri or successors of Missouri. Okay. So, in order to separate those, you need to also specify travel direction. Okay. So, essentially if you wanted to compute predecessor, then you will get all these rivers which directly or indirectly contribute water to Missouri. And in this case, your travel direction in some sense is opposite of these arrows. Okay. The other option is to find successors of Missouri, in which case we are following the arrows as they are represented in the diagram. And in this case, you might find Mississippi as a successor. Missouri contributes water to that. Okay. Let us next look at the tabular representation, because in SQL all the data has to be represented as tables. So, one way to represent graphs in terms of tables is to simply list the edges. Okay. So, here is a edge table for this river falls into another river graph, and in this case we may just need two columns. because each edge has a, it starts from a source and it ends up at a destination. So for example, if you are looking at the edge, Missouri falls into Mississippi, we may specify as a row where source is Missouri and destination is Mississippi. Now if I look at the other way around, Platte and Yellowstone, they fall into Missouri. In this case, Missouri may be the destination and those rivers may be the source. Okay. So if I actually created one row for each of these edges, then you are going to get a few more rows like this Ohio, etc., falling into Mississippi. They are here, and remaining contributaries to Missouri are here. Okay. So once you have this tabular representation, we can work with SQL and we can look at the syntax of this statement. Okay. So here is a very simple example of connect by. Okay. So in this particular select statement, you would recall some familiar things. So for example, there is a select clause and a from clause. These two we saw before when we were studying spatial querying, and you will remember that the from clause specifies the table. Okay. So in our case, let's say we are working with this table falls into representing our graph, that table may be named in the from clause, very much like the other SQL statements we saw where we were listing tables. Okay. Then we have two new clauses, this connect by and start with, and let's try to understand what they do. Start with is a much simpler clause, and in this case you notice it specifies a column in our table, that's the destination column, and it also provides a condition. So it's saying that you should start with rows in this table where destination is Missouri. So these two rows are the starting point, and starting with these rows we could either try to find predecessors of Missouri or successors of Missouri. Okay. So now a natural question is, what does connect by prior clause do? And you can probably guess it is specifying the direction of travel. Starting with Missouri, do you want the successors or predecessors? Okay. So in other words, if you think about this red arrow, if you want to go from destination to source, in other words getting predecessor, which rivers contribute water to Missouri, then you could specify this and as it is shown in this statement. So in fact, this prior is placed before source. So it basically says we are going from destination to source. Okay. We could move this keyword prior to other side after the equal sign, and that will give you the other direction where you are going from source to destination, and in some sense this arrow is going the other way. Okay. So, so let's look at both in side by side. If you are going from destination to source, or this should be source to destination, slight typo. So contributing rivers to Missouri in this case, so that you might see as the query we just saw. Okay. So this query is going to start with Missouri and get to the rivers which directly contribute to Missouri, and it will continue on and say any river that contributes to these rivers, Platte or Yellowstone, are also contributing to Missouri in an indirect way. Okay. The second choice is to ask the successors of Missouri, which rivers get water from Missouri. So if there were, let's say, a spill of some toxic material in Missouri, and you want to ask which other rivers should be observed or monitored for that material, then you will go the other direction. And notice here the prior keyword has been moved past the equal sign. Okay. So here the direction is from source to destination. This is a typo, but this is the other direction as shown in the figure. Okay. All right. So next, let's look at the semantics. Okay. As you know, SQL is a declarative language. It doesn't specify any algorithms to compute the result, but we can at least create a mock-up algorithm which is for hand simulation, so that you can understand the meaning of a given statement with connect by clause. Okay. So let's suppose we go back to this statement which we have seen before, where you're looking at this table falls into, and then you want to travel it in a certain direction and then get either predecessor or successors. Okay. So in order to execute it, the first step usually is to work with this initialization. This start with clause is executed first. So in this case, if you look at the query, the condition destination equal to Missouri, that will qualify two rows which are surrounded by blue box here. Okay. So we will initialize the result with just these two rows. Okay. So this is your result, or you can call it the prior result because it's going to grow. Okay. So, if the first steps we get 2 rows where destination is Missouri as specified by this start with clause. Okay. Once we have done that, then we can grow the result, and at that point this connect by clause comes in handy. So, in the next step we basically look at this connect by clause and this condition, and we try to grow the result. So, more formally what you can do is to think of this prior dot source equal to the original table falls into dot destination as a join condition. Okay. So, in other words, you can take a look at the prior source. Okay. In our result so far there are 2 sources, Platte and Yellowstone, and now we go back to original table falls into and say what do they match on the destination side, okay, as specified here. Okay. So, in this case, as you can see, it will match 4 rows in original table, and then all of these 4 rows will come and become part of your result. Okay. So, all of this will get added, and now your result has the original 2 rows and 4 new rows, 6 rows. Okay. Now, step 2 can be repeated again. All right. So, now we can again try to say, well, if I took all these sources P1, P2, etc., and try to match it with destination, will I get more things in the result? And in this case, as you realize, we are not going to add any more, because we do not have any predecessors of these new rivers P1, P2, etc., which has been added. Okay. So, we will terminate, and at this point we have all the rows of interest, and then finally the select clause is going to be executed, which will only take the first column, the source column, to form the result, and that is where you get the result. Okay. So, to summarize, we looked at connect clause which has been added to select statement by some vendors like Oracle to support graph queries. Okay. This particular statement allows you to work with a directed acyclic graph. So, if you have something hierarchical or tree like, then you can either travel up the tree or down the tree to compute predecessors or successors of a node. Okay. We also showed you an example with river network to explain the syntax and semantics. In the next video, we will come back and look at another statement called with recursive, which is more standardized in SQL3 and may be available across many brand names and vendors, and that will give you a more general statement to work with graphs. Okay. So, look forward to seeing you in the next video.